Okay, now we're going to talk about networking. We'll start with just some basic concepts. So if you have two nodes in a distributed system, two computers, uh, or two virtual machines for that matter, or containers, the only way that they can communicate is with a message. They send a set of bits from a sender to a recipient. Uh, Bits are bits, you need to be able to interpret it. So the message reflects an agreement between the sender and the recipient about the meaning of the bits. And there are protocols, there are standard agreements about the meanings of the bits. And a portion of the boot process is connecting to the network through a network adapter, either Wi-Fi or cable. So the network is logically divided into four layers, and each has a collection of protocols. There's something called the ISO 7-layer model, which is dated, and people will argue with this, but it's really not used. If you look at the layers and the protocols, you have the application layer, and some of these may be familiar to you. HTTP is a application level protocol. Uh, IMAP is used for email. LDAP is used to manage users, and so on. There are transport protocols. There's TCP is the most common. UDP gets used if you want to broadcast something. Uh, there's internet level protocols, two different versions of IP, excuse me, which we'll talk about, a couple others. And there are data link, so physical transport. There's Ethernet, there's ATM, DSL, and those are for actually moving the bits. So in general, your device is on a local network and it may use one type of protocol, and you want to send a message to a device on another local network, possibly through a third network. Okay, so how does this work? Well, there's a gateway. So a gateway connects two networks and converts the information, the data, and the other communications between the protocols used by these two networks. So it's got to know the protocols. There's a special kind of gateway called a firewall, and that monitors incoming and outgoing traffic and either permits or blocks data packets. And these are configurable, and you would specify some rules how to configure a firewall. Another type of data of gateway is a proxy, and that manages internet traffic on your behalf. You, in this case, is a service. And so there's a special kind of proxy called a proxy server, which will hide your IP address from the outside world. And pictorially, how does this work? There are all kinds of networks. There's the cloud, the network the cloud provider provides. Uh, there's the network in your home. There's the network in your corporation or university. There's the phone network, and they all are make up the internet or connected through the internet. I mean, they're all pieces of the internet. And so then, you see a gateway connecting these things. And here's how gateways are used with the cloud. You send a message, presumably it's encrypted, goes to the cloud gateway, which may does some identity checks, and then passes it on to the service that you're trying to reach. There's also some logging. There are things that go on while it's inside the cloud, but basically you send a message to the cloud through a gateway. And so there's some myths about networks, uh, and Sun Microsystems, 30 years ago now, made a list of this. So one is the network is reliable. It's not. It has failures like anything else. Networks made up of computers and wires, and both computers and wires fail. Latency is zero. No, it takes time. It takes time to move the bits. I mean, uh, bandwidth is infinite. No, that's also not true. Bandwidth is finite. You have a certain amount of bandwidth depending on how you're connected to the internet. The network is secure. Okay, well, we'll talk about that. That's not true at all. People can eavesdrop. People can spoof. There are all kinds of things you can do uh, in the network. The technology doesn't change. Well, it's like everything else. So I mean, that's the fundamental message of these myths, that it's like everything else. The technology does change, and the people that administer the network have to adapt. And the assumption is, again, a myth, that there's only one administrator. It's not true. There is an overseeing organization for some parts of it, and we'll talk about that. But in general, that the different parts of the internet have different of the network have different administrators. Transport cost is zero. Now, I mean, you're going to use computers. Okay? So computers cost money. So the transport cost money. The network is homogeneous. Well, that's false as well. There are different. There are routers inside the network. They may have different manufacturers. There are different types of computers that are specialized. It's a heterogeneous network. So those are things that affect people's understanding about networks. So again, some offline discussion questions. What's the benefit of viewing the network as a collection of layers? What good do these layers do? Why would you use one protocol in a given layer instead of another? Well, what are the factors that would guide your choice of protocols? And what are the limitations of using messages as a communication mechanism? I said that's the only way to communicate. What are the limitations? Okay, so let's talk about connecting to a network. So this is preliminary to sending a message. Before you can send a message from your laptop, you have to connect to the network and you have to get an IP address. So connecting to a wireless network, there's a wireless router somewhere in your neighborhood and it's broadcasting. Uh, and you need to connect to it. And each router has what's called a MAC address. And I don't remember what MAC stands for, machine something something. And your laptop has a network adapter. And so the network adapter is a radio receiver, among other things. So it will listen to the broadcast of the wireless router, and then it will generate responses. And your network adapter has a MAC address. And so there's a protocol. Again, you have to make sense of the communication, and there's a family of standards that go under the label 802.11. So there are a number of versions of 802.11, and it uses the data link layer of the internet protocol, so that's down at the bottom. And the process of connecting involves exchanging MAC addresses between your laptop and the wireless router. And then you need to get an IP address. Okay, so you get an IP address from the DHCP server. So remember, that's another protocol, DHCP. And that's either in your router at home or it's an actual server on an enterprise. And routers know the address of the DHCP server. So if you're in an organization and you turn on your computer, then it talks to the router. The router knows how to talk to DHCP, and that's the mechanism you use to get an IP address. So the laptop knows the MAC address of the router, and then the router knows the address of the DHCP server. Then your laptop can request an IP address from the DHCP server using the DHCP protocol. So your laptop broadcasts a message, and it goes to the DHCP server, which has a collection of IP addresses, and it allocates one to your laptop. So where does this collection of IP addresses come from? It comes ultimately from an organization called ICANN, the Internet Corporation for Assigned Names and Numbers. It's a nonprofit organization and it has a responsibility for assigning domain names, assigned names, and IP addresses. Those are the numbers. It allocates allocates addresses in large blocks. So it specifies the first digit, and then all the other things that follow the first digit are in a block, and it will do that to regional entities or to the U.S. military, since this scheme was set up when the military was inventing. I don't know, initiating the internet protocols. So a recipient of one of these large blocks will split up the block and further allocate it, and it goes down till one of the smaller blocks is given to your DHCP server. So your DHCP server has a list of IP addresses that it can allocate. And so every device is assigned an address. So that's true of virtual machines. Containers, when we talk about containers, are actually packaged into pods, and pods get IP address, but you can think of it as a container having an IP address. The Internet of Things, okay, things like toasters and refrigerators and thermostats get IP addresses. So let's go into IP addresses. So you remember the third layer of the four layers was had two different versions of IP, and so IPv4 has 32 bits. IPv6 has 128 bits. The 32 bits have been exhausted. Uh, and IPv6 was standardized in 1996, which is what, almost 30 years ago. And if you represent an IP address in IPv4, it's a sequence of four numbers where each number is a decimal number between 0 and 255. And you might try and get the IP number of your laptop, for example. And IPv6 is 8 groups of 4 hexadecimal numbers, and colons are used as a separator. If you look at IPv6 and its adoption rate, uh, it's now 2024 when I'm recording this, and it's maybe 45% used. So one of the discussion questions is, it's 30 years old. Why did it take 40 years, 30 years to reach 46% or whatever the percentage is here? And another discussion question is, so one discussion question is, why did it take so long? And another discussion question is, why would you, how did IPv4, which was exhausted maybe 4 or 5, well, maybe longer, which all the IP4 numbers have been allocated, how was it managed to handle the growth in the internet since all the numbers were exhausted? And so your your ISP has a collection of IP addresses, and it delegates some to your DHCP server. But each address is either public or private. A public IP address is available from anywhere in the internet. So anywhere in the world, you get on the internet, you have a public IP address, and you can put it you can send a message to that. A private IP address is restricted to your local network. So private IP addresses can be replicated. And each address is either static or dynamic. A static IP address is permanently assigned. A dynamic IP address is generated at boot up, and it's temporary. So private IP addresses are the ones starting with 10, the ones starting with 172, some of them, the ones starting with 192, again, and 192.168. Why those choices, I do not know. 127.0.0.1 is a special private address. It's reserved for what's called localhost. So if you send a message to localhost, then it gets returned to your browser or to whoever sent it to your machine as a message, and you use that for testing. So you do something, and now you want to, so let's say you create a web page and you want to see what it looks like. Well, you can you can invoke that web page from put 127.0.0.1 in your browser, and that will invoke that web page on your machine without going over the internet. Uh, your ISP has been allocated a collection of IP addresses, and through your DHCP server, it will allocate one to your device when you log in, and that will remain your IP address until you log off. And the DHCP server uses the DHCP protocol, and that's how it assigns. So your local network has a DHCP server. Again, it's in the router, or if you're in an enterprise, it's a special server, but your router knows about it. And the DHCP protocol essentially broadcasts saying, I need an IP. I have a client here, and client needs an IP address, and it has a pool. Or if the pool gets exhausted, it'll go back to the ISP and say, I need some more. So when you compose a message has a header and a payload, and so you want to send an HTTP message over TCP/IP. And so the HTTP message is the payload of the TCP protocol, TCP message, which is going to be sent using the TCP protocol. The TCP message is the payload of the IP address. So the analogy is using the mail system. So you want to send a message to an individual. You put it in an envelope. That's the application level protocol. The envelope is put into another envelope with the house number that you want to send them to. That's the next layer in the that's the next layer in the four-layer protocol. That envelope in turn is put in an another envelope with the post office address. Okay, and that's the internet level of the four level, and that outer envelope is sent from post office to another post office, and it's open. Okay, and then what it finds is the envelope you put in there, and that gets delivered to a house. And then someone in the house opens that envelope and finds another envelope with with the name of a person, and it sends it to it. So that's the analogy that the payload of one protocol is a message in another protocol. And so every message has a header and a payload. In particular, the IP protocol does. And the header consists of the IP address of the source and the IP address of the destination. So this is what it looks like if it's IPv4. You see there's the source and the destination. There's other stuff in there. And this is what it looks like for IPv6. Again, there is a source and destination and other things in there. So a device creates a message by creating a header and the payload and sending it on the network. And so IPA sends a message to IPB, and it consists of a header and a payload. And then when IPB gets the message and needs to respond, it responds to the source address in the header. But that source address may not be the original sender. So when IPA sends a message to IPB, which includes a payload, um, then a gateway can make it look like the message comes from the gateway by changing the source. And so the response will come back to the gateway, and the gateway has to have a message to manage the response and send it back to the original sender. So discussion questions, again for offline, why has the adoption of IPv6 been so slow? Is the DHCP server on your local network, or is it on the ISP's network? And remember, the gateway has to have a mechanism to send it back to the right sender. What are some mechanisms it might use? Okay, moving on to DNS. So IP addresses are too cumbersome for people to use. And so there is a thing called a URL, Uniform Resource Locator, and that's what's used to identify a device. And then a directory service is used to map from the name, from the URL, to an IP address. And you can think of a phone book as having names and phone numbers. And this is managed by the domain name system, DNS. And that's a global directory service for virtual machines. And it's managed by ICANN. Remember, ICANN manages names and numbers. So how does this work? You send a URL to a DNS server. DNS server takes as input the URL and returns an IP address. And then you use that IP address, or you being the client, uses that IP address to send a message to the site. Okay, so you send in the picture, you send it website.com. It sends you back 1, 2, 3, 4, 5, 6, 7, 8, 9. You then send a message where the destination IP is 1, 2, 3, 4, 5, 6, 9. Oops, 6, 7, 8, 9. So clearly it's not that simple. Uh, Messages are transmitted from one computer to another, going through multiple servers. There are multiple DNS servers. There's a hierarchy of DNS servers, and the picture showed a single line, but in fact, there's a network of routers that transmit the messages, and getting into that is way more detailed than we're going to go into now. You can do some research if you're interested and find out, more how the internet routing works. And this is a way of sharing the load and making sure that various pieces don't get overloaded. So let me talk about the hierarchy of the DNS. So if you look at the URL www.mse.isr.cmu.edu, and if you had all the if all this was one server, then the server would get overloaded from requests, and it would hold a lot of mappings. And so it's arranged as a hierarchy. So you start with a root server, and there are 13 root servers and they have known addresses. They're built into your router, and if you follow this URL, you can get to what specifically the uh, IP addresses of the root servers are. And then what happens is the root server gives you the IP address of the .edu. So if you look at that URL that you're looking for, then the rightmost thing is .edu. You find the address of .edu from the root server. Then you look on .edu and you find the address of CMU. And then you look in CMU and you find the address of ISRI. And then you look in ISRI and you find the address of MSE. And then you look in MSE and you find the address of www. And the purpose of this is to enable local control over the leftmost entries without having to affect the hierarchy. So I could change www to www.mse, and no one needs to know that but the MSE server. I don't have to communicate that up the network. And so this is where the root servers are. They were assigned historically, so you see they're very heavy in the US, and a couple in Europe, and one in Asia. Okay. But the root servers are mirrored. These are not the only servers with those addresses. So each root server has multiple copies of it scattered around, and that enables coverage all over the globe. Uh, as you might expect, the DNS server system is highly secured. Uh, so if an attacker could manipulate the DNS server, then they could disrupt or intercept or do something bad with the one portion of the internet. They could shut down the internet. And so the servers are extensively physically secured. You can't go look at them. You need to have right access. And they're also extensively secured from an internet perspective. So they're both physically secured and logically secured. And other servers are also secured. It means that changing an IP address within a DNS server is restricted to authorized personnel. And we'll talk about DNSSEC in a minute, but that's another means of securing the DNS system. It's a different type of information. Okay, so clients do not access the DNS server for every request. It would generate too much internet traffic. And so associated with each DNS entry is something called time to live, TTL. And it's also called refresh interval. And it's different than the time to live in the protocol. So that gets a little bit confusing if you push into this. And the client or the ISP caches the IP address. So caching is a way of cutting down on the amount of traffic. So dot the root server caches the .edu server, the .edu server caches the .cmu server, the CMU server caches the address of the .isri, and so on. So there's a lot of caching going on so that they don't have to make internet requests to get that. And the value of the time to live depends on where in the hierarchy you are. High in the hierarchy, the authoritative servers, they're set to 7 days. That's the maximum, since the likelihood of there being a change is small. Records under local control can have their TTLs set low, could be seconds or minutes. A critical thing about the time to live is that the smallest it can get is 1 second. So in the next lecture soon, we're going to talk about containers. And containers come and go quickly, so 1 second is not an adequate amount of time for a container to live. And so DNS doesn't work for containers very well. Yeah. So from the your client's perspective, the client has the gets the IP address of the EDU server. Again, the client would go to the root, it would come back to the client and give it the address of the EDU server. And then the client would go to the EDU server and get the address of the MSE of CMU and so on. And it would cache these things. So the TTL is the root server or the EDU server is 7 days. The IP address of CMU is probably, I'm guessing, is probably 7 days. And now we get down to maybe a couple hours, and then we get the address of the www server locally, and that might be 5 minutes. And this doesn't mean that it's going to be replaced in 5 minutes. It means that you can trust the cache address that you get for 5 minutes. And these are estimates. One of the possible assignments that you may be doing would be to get the actual numbers. Now you can use DNS to handle overload and failures. So we'll talk about this later, but failure is sort of endemic in the cloud. You need to worry about it. And so the servers could fail, uh, and the servers could also get overloaded. And so the picture that I showed a couple slides ago showed one number coming back. There could be multiple numbers. There could be multiple servers with different IP addresses with the same URL. And then the DNS server can rotate this. So it gets a request and it'll send them back in the order 1, 2, 3, gets another request from someone else and it can send it back in the order 2, 3, 1, and so on. So the client would access the URL that it's looking at with the first response. If that works, it's happy. If not, it has a fallback. It's the second response. So one advantage of this is to manage failure. A second advantage is to manage overload. Again, it doesn't respond. And it's a way of sharing the load among the different clients and the different servers that have the same URL. So discussion questions, and I told you the answer to this. Why is DNS primarily for virtual machines and not for containers? And what's the sequence of IP address in your device from the root to getting to your device? So again, your device is registered and it goes through a sequence of IPs someone would go through a sequence of IPs to get to your device. What are they? So let's now move on. We'll talk about ports. So IP addresses get messages to servers, to a service, uh, or to a virtual machine. I'm sorry, or a container, or actually a pod, and it still has to go to a service. So the message has gotten to the virtual machine, and it needs to send it to a service, and the service is listening for the message on a port. Okay, so what's a port? You can think of a telephone switchboard in a hotel if you're old enough to understand what that is. So a call comes into the hotel. On the hotel number, there was a person that would answer the hotel so and so, and you would say, I want to talk to room such and such, or I want to talk to a person, and the operator would look up that person and find out what room they're in, and then they would take a cord and plug it into that room number. That would cause the phone to ring in the room, somebody would answer it, and the communication would go on through that cord. And that's what ports do. A service listens to a message on a port. A message comes into the virtual machine. It has to figure out what port number it wants, and that's the purpose of the TCP protocol. And then it sends it to that port, and there is a service that's listening for messages on that port. So each service listens on one or possibly multiple ports. And some port numbers are restricted and they're assigned by ICANN. So there's one for secure shell, there's one for mail service, there's one for DNS, there's one for HTTP, there's one for HTTPS, and those are designated ports. So A, no one else can use it, and B, if you want to send to, let's say, a web browser, you would send it on port 80 or port 443, depending on whether it's secured. Other port numbers are by agreement. And so the operating system forwards the message to the specified port. The service that's listening to the port gets that message. So a message intended for a virtual machine uh, goes through a hypervisor and goes to the virtual machine. Okay, so that has an IP address. And then within that, the operating system figures out what the port number is and sends it to the app. Now, when you're doing a container, it gets a little messier. So you have a container, it sits on an operating system. It operating system decodes the port. It tells the container runtime engine what port it is. And it's possible that several applications are listening on the same port. So you might have a web browser running, two different web browsers from two different vendors running in being two different applications. They're both listening on port 80. And so which one gets the message? Okay, so sending messages to containers is not as what is general as sending message to a virtual machine. And so you have to do something to route those messages. And that's port forwarding. So port forwarding tells the operating system, if you get a message from a virtual machine, if you get a message for me on port 80, I really can't listen on port 80 because someone else has grabbed off port 80, so send it to port 8080, for example. So again, some discussion questions. What are some other dedicated port numbers? Some of them are fairly archaic at this point. And what port numbers aren't assigned? And those are used by agreement between the sender and the recipient. Uh, Moving on to talk about bridged and NAT networks. So you have a virtual machine. It has it lives on a host computer, which has a hypervisor. Each virtual machine on that hypervisor has a IP address. A bridge network, all those IP addresses are exposed. Okay, so on a bridge network, the IP address of that the virtual machine was assigned is exposed to the outside world. It can be public or but it will be attached to a message sent. And then when somebody responds to it, it'll get to the right place. So each virtual machine has its own IP addresses. These IP addresses could be private or public, but if it's on a bridge network, uh, it may or may not be behind a gateway. So let's ignore that for a minute. And those virtual machines with public IP addresses can be directly accessed. If it's behind a gateway, then the gateway would send it to it. The gateway would be external to the hypervisor to this machine. The gateway would be over the network that this physical machine is on. NAT network is different. So NAT is a piece of software, and it acts as a gateway for the virtual machines and for their IPs. So this makes the IPs in the virtual machine all private. And so the NAT is connected to a host network to the in the hypervisor, and it acts as a firewall. It could act as a firewall. So a message comes in, it goes to the uh, hypervisor. The hypervisor has to translate that into a message for a particular virtual machine, since those virtual machines are private. So again, uh, discussion questions. So the slides, the two pictures that I show that bridge networks are type 1 and NAT networks are type 2 hypervisors. Is this necessary? And the slides show how messages are routed for virtual machines. What would the corresponding pictures be for containers? Now moving in on to TCP, so we introduce the notion of port. So ports are included in the transmission control protocol, TCP, and that's a transport layer protocol. And it's commonly wrapped as a payload and IP, so you see TCP over IP. And it's got a source port and a destination port. And TCP is a reliable protocol. What that means is that you have to send an acknowledgement so that the message is guaranteed to be delivered. If you don't get an acknowledgement within a certain amount of time, you send it again. And if you don't get an acknowledgement again, you assume the message has failed, but the client knows what's going on. A IP message is what's called fire and forget. So the sender of an IP message doesn't get doesn't get an acknowledgement. It may get a response, it may not, but it has to decide that if it doesn't get a response, it has to decide that it might to retry it. Whereas TCP is explicitly an acknowledged response. The second thing is that TCP is ordered. So things get scrambled when they go off into the internet. So messages are broken into packets. Packets are a certain size. They may take their own routes, and they may arrive in a different order. Well, TCP, you actually have a sequence number so that the recipient will put the sequences together. TCP has error checking handling. Okay, so it uses a checksum. If you don't know what checksum is, you should look that up. Pretty straightforward. Uh, and the header includes the source port and the destination port, and they can be, the destination port tells the recipient operating system how to route it. Uh, the source port tells the destination how to respond. They both can be modified the same way that IP addresses could be modified. So discussion questions. Is it possible to use TCP on an internet layer protocol other than IP? I said the common thing is TCP over IP. Is it required to use IP? And secondly, how long does the sender wait for an acknowledgement? And, so it usually means you could look that up. You might take a guess first. Okay, and then finally, let's talk about structuring your network. So there's a concept called a subnet, which is a group of devices that are connected directly to each other. And so messages between devices on a subnet don't have to go through an IP router. And it's created within an address space by making the first portion of the IP address, the subnet prefix, the same for all the devices in the subnet. And then the remaining portion of the IP address is identify the uh, particular device. Why do this? One is network performance. It makes routers go faster. You don't have to use them. It simplifies the work of a router. Second is security. A firewall for the subnet can verify the resources that requests on that resource to that subnet are allowed. And it makes life easier for the system administrator having subnets because it can manage the system administrator can manage a collection of devices all at the same time. And so you partition your network partially through subnets, partially through firewalls, and it protects one portion of your network for another. So, for example, the financial systems of your organization might be separate from the normal activities of the other employees. And that would be protected so that the other employees can't get at the financial systems, even if they know the address. And there's also a way of using partitioning your network in terms so that that's inside the intranet. Intranet is the network of your organization. There's also a way of separating the intranet from the internet. So the internet is everything, and the intranet again is your organization, and that's called demilitarized zone. So they're used to allow internet access from anybody to some servers and not to the intranet. So web servers, for example, are externally visible. You want everybody to access the web server that describes your organization. So you'd put it in the DMZ, you'd make it accessible. Also, you can get at your intranet securely, and that's done using a virtual private network, a VPN. And the server for the VPN would be in the DMZ. So here's a picture of that. So a message from the internet goes through a firewall. If it's sent to port 80 or 443, it's passed to the web server. I forgot what the designated port for VPNs are, but there is one, and it would be passed to the VPN server. And if it is not one of the designated ports in the firewall, it would be passed to the second firewall, which might reject it uh, or might pass it on. And so the DMZ has rules for routing. And these rules would include where to send requests to certain ports. Now, virtual private networks use a technique called tunneling. And so that what virtual private network does, it allows you from your home or some other place to log into the intranet, and be treated as if you were inside the physical boundaries of your organization. And so you log into the VPN server, which is in the DMZ. You give it your credentials. These credentials are verified. They could be passed to an authorization mechanism in the intranet, or it could be that the VPN server has its own way of authorizing you. And then once you're authorized, it sets up a tunneling program so that subsequent messages are sent using a tunneling protocol. So you have a piece of software on your machine that's a VPN. I want to say server, but the server's on the other side. So it knows about VPN. It's a VPN client. So the tunneling protocol encrypts your entire message, including the IP. So you want to send a message to a machine, to something, and have it pretend that it comes from the intranet. So first that message is encrypted, and then it's wrapped, uh, uh, and it becomes the payload of another message that is sent to the VPN server. So assuming you have the appropriate credentials that you've been authorized, then the VPN server will decrypt it and send it through the firewall to the recipient. So one of the rules on the second firewall in the DMZ is if it comes from the VPN, then pass it through. So if your destination is within the intranet, then it's just passed. If your destination is in the internet, then it is managed by a proxy and it's sent out again. Uh, and through to the internet, but it looks like it came from a machine inside the intranet, and there's a gateway there and a proxy that protects the IP addresses. So discussion questions. So what does your organization's intranet look like? How many firewalls are there? What subnets are there? Uh, in addition to routing, second question, in addition to routing rules based on port numbers, what other rules are there in a firewall? And distinguish that between the internet firewall and the one that protects the intranet. And that's the end of this chapter.